Welcome to the edge of spacetime itself, where the familiar laws of physics twist into something almost unrecognizable. Tonight, we journey to perhaps the most mysterious and captivating phenomena in our universe, the event horizon. This invisible boundary marks the point of no return around black holes, where space and time become so warped that even light cannot escape. It's a place where our understanding of reality reaches its absolute limit, where the very fabric of existence reveals its most profound secrets. Hey there, how are you tonight? No matter what time it is or where you're watching from, I'm glad you're here. I'd love to know where you're listening from tonight. Drop a comment below. The visuals are here for you, but feel free to close your eyes, breathe deep, and let your imagination do the floating. I would love and encourage you to watch the video till the end to learn many new things, but there is absolutely no problem if you doze off midway through the video. Also, I would encourage you to subscribe to this channel and leave a like on this video. If you love coming across this channel more often, it helps the algorithm find more sleepy minds and souls like us who have an amazing curiosity and love for science in their minds. Let's begin. You're an astronaut approaching a black hole, that cosmic monster whose gravitational pull is so intense it devours everything that comes too close. As you drift closer, you notice something peculiar. Time itself begins to slow down relative to the outside universe. What feels like minutes to you becomes hours to observers watching from a safe distance. You're experiencing the profound effects of Einstein's general relativity in its most extreme form, where massive objects literally bend the geometry of space-time itself. The event horizon isn't a physical surface you could touch or see. It's more like an invisible sphere of influence surrounding the black hole's singularity, that mysterious point at the center where matter is compressed to infinite density, and the laws of physics as we know them simply break down. The size of this horizon depends entirely on the black hole's mass. For a black hole with the mass of our Sun, the event horizon would have a radius of about 3 kilometers. But for the supermassive black holes lurking at the centers of galaxies, these horizons can stretch for millions of kilometers. What makes the event horizon so fascinating is its relationship with the speed of light. We often think of light as the fastest thing in the universe, racing through space at nearly 300 million meters per second. Nothing can travel faster than light, according to Einstein's special theory of relativity. Yet at the event horizon, even light moving at maximum speed cannot escape the black hole's gravitational embrace. This creates a boundary in space-time beyond which no information can ever reach the outside universe. The mathematics behind this phenomenon are both elegant and terrifying. The event horizon's radius, known as the Schwarzschild radius, is calculated using a surprisingly simple formula that relates the black hole's mass to the speed of light and the gravitational constant. For any object, if you could compress it down to its Schwarzschild radius, it would become a black hole. For Earth, that radius would be about 9 millimeters. For the Sun, it's those 3 kilometers we mentioned earlier. But here's where things become truly mind-bending. From the perspective of someone falling toward a black hole, crossing the event horizon doesn't feel particularly special. You wouldn't notice any dramatic change as you pass through this invisible boundary. Time flows normally for you, and you continue falling toward the singularity. However, for anyone watching you from a safe distance, something extraordinary happens. As you approach the event horizon, you appear to slow down dramatically. The light from your body becomes increasingly redshifted, stretched to longer and longer wavelengths until it fades beyond the visible spectrum. From their perspective, you never actually cross the event horizon. You appear frozen at the boundary, your image growing dimmer and redder until it disappears entirely. This strange duality reveals one of the most profound insights about black holes and space-time itself. The event horizon represents a fundamental limit to observation and communication. It's a one-way membrane through which matter and energy can pass inward, but from which no information can ever escape outward. This creates what physicists call the information paradox, one of the deepest unsolved problems in modern physics. The discovery of black holes and their event horizons represents one of humanity's greatest intellectual achievements. It began with Einstein's field equations, published in 1915 as part of his general theory of relativity. These equations describe how matter and energy curve spacetime and how this curvature affects the motion of objects. Within months of Einstein's publication, a German physicist named Karl Schwarzschild found an exact solution to these equations, describing the spacetime geometry around a spherically symmetric, massive object. Schwarzschild's solution revealed something unexpected. If an object became sufficiently dense, it would create a region from which nothing could escape. At the time, this seemed like a mathematical curiosity rather than a physical reality. Even Einstein himself was skeptical that such objects could actually exist in nature. The term black hole wasn't coined until 1967 by American physicist John Wheeler, who recognized that these objects weren't just mathematical abstractions, but real phenomena that could be observed and studied. The first indirect evidence for black holes came from observations of binary star systems, where invisible companions were stripping matter from visible stars. As this matter spiraled inward, it formed an accretion disk that heated up and emitted X-rays. The amount of energy released and the orbital dynamics of these systems could only be explained if the invisible companion was a black hole. But it wasn't until 2019 that we finally captured our first direct image of a black hole's event horizon, using the Event Horizon Telescope to photograph the supermassive black hole at the center of galaxy M87. The nature of the event horizon challenges our most basic assumptions about reality. In our everyday experience, we're accustomed to the idea that space and time are fixed, absolute quantities. We imagine a universal clock ticking away the seconds, and a cosmic grid of space through which objects move. But general relativity reveals that space and time are dynamic, flexible quantities that respond to the presence of matter and energy. Near a black hole, this flexibility becomes so extreme that it creates regions where the normal rules of cause and effect break down. Consider what happens to the concept of simultaneity near an event horizon. In our everyday world, we can meaningfully talk about events happening at the same time in different locations. But near a black hole, the curvature of space-time becomes so severe that simultaneity becomes observer-dependent in extreme ways. Events that appear simultaneous to one observer may be separated by vast amounts of time for another observer in a different reference frame. The event horizon also raises profound questions about the nature of information and consciousness. If you were to fall past the event horizon, your experiences and observations would be forever cut off from the rest of the universe. From your perspective, you would continue to exist and experience the universe, but that information could never be communicated to anyone else. This creates fascinating philosophical puzzles about the nature of reality and observation. One of the most intriguing aspects of event horizons is their relationship with thermodynamics. In the 1970s, physicist Stephen Hawking discovered that black holes aren't perfectly black. Due to quantum effects near the event horizon, they actually emit radiation and gradually evaporate over time. This Hawking radiation has a temperature that's inversely proportional to the black hole's mass. For stellar mass black holes, this temperature is incredibly small, far colder than the cosmic microwave background radiation. But for tiny black holes, the temperature could be enormous. The discovery of Hawking radiation revealed that event horizons have thermodynamic properties similar to ordinary matter. They have temperature, entropy, and they can exchange energy with their surroundings. The entropy of a black hole is proportional to the area of its event horizon, not its volume. This relationship, known as the holographic principle, suggests that all the information contained within a black hole might be encoded on its two-dimensional surface. This leads us to one of the most profound mysteries in modern physics: the black hole information paradox. When matter falls past an event horizon, it carries information about its quantum state. But if black holes eventually evaporate through Hawking radiation, what happens to that information? Quantum mechanics suggests that information cannot be destroyed, but general relativity seems to imply that information falling past the event horizon is lost forever. Resolving this paradox may require a complete revolution in our understanding of spacetime, quantum mechanics, or both. Recent developments in theoretical physics have proposed various solutions to this paradox. Some theories suggest that information might be preserved in subtle correlations in the Hawking radiation. Others propose that the event horizon itself might be more complex than we initially thought, perhaps containing a firewall of high-energy particles that would destroy anything attempting to cross it. Still, others suggest that the interior of a black hole might be connected to other regions of space-time through wormholes or higher dimensional structures. The study of event horizons has also revealed connections to other areas of physics that initially seemed unrelated. String theory, which attempts to unify quantum mechanics and general relativity, predicts that black holes might be described by collections of tiny vibrating strings. Loop quantum gravity suggests that the singularity at the black hole's center might be resolved by quantum effects, potentially creating a bounce that connects our universe to other regions of space-time. As we continue to probe the mysteries of event horizons, we're discovering that they serve as natural laboratories for testing our most fundamental theories about reality. The extreme conditions near black holes allow us to explore regimes where quantum mechanics and general relativity both play important roles, potentially revealing new physics that could revolutionize our understanding of the universe. The technological achievements required to study event horizons directly are staggering. The Event Horizon Telescope that captured the first image of a black hole's shadow required coordinating radio telescopes across the entire planet, creating a virtual telescope the size of Earth. The LIGO gravitational wave detectors that first observed black hole mergers required measuring distortions in space-time smaller than 1/10,000th the width of a proton. These achievements represent humanity's ability to probe the most extreme environments in the universe using our most sophisticated technology and deepest theoretical insights. Looking toward the future, our understanding of event horizons will likely continue to evolve as we develop new observational techniques and theoretical frameworks. Proposed space-based gravitational wave detectors could observe black hole mergers with unprecedented precision. Advanced computer simulations are revealing new details about the behavior of matter and energy near event horizons. And theoretical developments in quantum gravity may finally resolve the paradoxes that have puzzled physicists for decades. The event horizon represents more than just a boundary around black holes. It's a frontier of human knowledge, a place where our understanding of reality reaches its limits and new discoveries await. As we continue to explore these cosmic mysteries, we're not just learning about black holes, we're uncovering fundamental truths about the nature of space, time, matter, and information itself. Tonight, as you drift towards sleep, remember that you're part of a universe filled with wonders that challenge our deepest assumptions about reality. The event horizons surrounding black holes are gateways to understanding the most profound mysteries of existence. They remind us that the universe is far stranger and more beautiful than we ever imagined, and that the journey of discovery is just beginning. Now we venture into the realm where space and time themselves become distorted, where the very fabric of reality bends and warps under the influence of extreme gravitational forces. We've journeyed through the gentle choreography of planetary orbits and the vast architecture of galactic clusters. But now we must confront gravity's most dramatic and mysterious manifestation, the event horizon itself. Picture, if you will, a region of space-time so profoundly curved that it creates a boundary from which nothing, not even light, can escape. This is the event horizon, the point of no return around a black hole where the normal rules of physics, as we experience them, begin to break down in the most extraordinary ways. It's here that Einstein's vision of curved space-time reaches its most extreme expression, creating phenomena that challenge our deepest understanding of reality. The event horizon isn't a physical surface you could touch or see. Rather, it's a mathematical boundary, a sphere of influence surrounding the black hole's singularity, where space and time become so distorted that cause and effect, past and future, begin to lose their familiar meanings. The size of this boundary depends entirely on the mass of the black hole itself. For a black hole with the mass of our Sun, the event horizon would have a radius of just 3 kilometers. For the supermassive black holes that anchor galaxies, containing millions or billions of solar masses, the event horizon can stretch for millions of kilometers. What makes the event horizon so fascinating is how it reveals the intimate connection between gravity, space, and time. As you approach a black hole, time itself begins to slow down relative to distant observers. This isn't science fiction, but a direct consequence of Einstein's general relativity, confirmed by countless observations and experiments. An astronaut falling toward a black hole would experience time normally from their perspective, but to someone watching from a safe distance, that astronaut would appear to slow down dramatically as they approach the event horizon. This time, dilation effect becomes so extreme near the event horizon that, from the outside observer's perspective, the falling astronaut would appear to freeze at the boundary, their image growing redder and dimmer as their light is stretched by the black hole's immense gravity until it fades from view entirely. Yet from the astronaut's perspective, they would pass through the event horizon in finite time, experiencing nothing particularly special at that moment, though their fate would be sealed. The event horizon also creates one of the most profound puzzles in modern physics, the information paradox. According to quantum mechanics, information cannot be destroyed, yet anything that falls past the event horizon seems to be lost forever, taking its information with it. This apparent contradiction has sparked decades of theoretical investigation and has led to some of the most exotic ideas in physics, from the holographic principle to the concept of black hole complementarity. Perhaps most remarkably, the event horizon represents a kind of cosmic membrane, where the quantum nature of space-time itself becomes apparent. Near the event horizon, the vacuum of space begins to behave in strange ways, with virtual particles being separated and real particles being created from nothing. This process, known as Hawking radiation, causes black holes to slowly evaporate over time, returning their energy to the universe in the form of thermal radiation. The study of event horizons has also revealed deep connections between gravity, thermodynamics, and information theory. Black holes have temperature and entropy, with the entropy proportional to the area of the event horizon, rather than the volume enclosed. This suggests that the information about what falls into a black hole might be encoded on its surface, leading to the revolutionary idea that our three-dimensional reality might be a projection of information stored on a two-dimensional boundary. As we contemplate these cosmic boundaries, we're reminded that the universe operates according to principles far stranger and more wonderful than our everyday experience suggests. The event horizon stands as a testament to the power of mathematical physics to reveal hidden truths about reality, showing us that space and time are not the fixed stage upon which physics plays out, but dynamic, malleable aspects of existence that can be stretched, compressed, and even torn. In the gentle darkness of approaching sleep, we can marvel at how the same gravitational force that keeps us safely anchored to our beds also creates these most extreme environments in the universe. The event horizon reminds us that reality is far richer and more mysterious than we might imagine, filled with boundaries we cannot cross, and phenomena that exist at the very limits of physical possibility. Here, at the edge of the known universe, gravity writes its most dramatic poetry in the language of curved space-time and quantum uncertainty. Welcome to the quiet corner of the cosmos where we unravel the mysteries of the event horizon. Tonight, we journey deeper into these enigmatic boundaries, exploring the profound questions that emerge when matter and energy encounter the ultimate point of no return. As we've established, the event horizon represents far more than a simple boundary. It's a realm where our fundamental understanding of physics reaches its limits, where the familiar rules of space and time bend beyond recognition. But tonight, we venture into the deeper mysteries that surround these cosmic gateways. Consider this remarkable fact. Every black hole, regardless of its size, possesses what physicists call a photon sphere. This invisible boundary exists just outside the event horizon, roughly 1.5 times the Schwarzschild radius. Here, light itself can orbit the black hole in perfect circles, trapped in an endless dance around the gravitational well. Imagine photons of light, traveling at their maximum speed, yet unable to escape, forever circling in this cosmic carousel. The photon sphere reveals something profound about the nature of space-time near black holes. It's not just that gravity becomes strong enough to trap light at the event horizon. Rather, the curvature of space-time becomes so extreme that even before reaching the event horizon, light begins to follow increasingly curved paths. This creates a gradient of gravitational influence that extends far beyond the black hole itself. Within this photon sphere, something extraordinary happens to the concept of causality. In our everyday experience, cause precedes effect in a linear fashion. But here, the extreme curvature of space-time creates closed, time-like curves, theoretical paths through space-time that could, in principle, allow an object to travel into its own past. While these remain theoretical constructs, they highlight how black holes challenge our most basic assumptions about the nature of time and causality. The mathematics describing these regions becomes increasingly complex as we approach the event horizon. Einstein's field equations, which elegantly describe the curvature of space-time, begin to reveal their most exotic solutions. The Kerr metric, which describes rotating black holes, introduces additional complications. These spinning black holes drag space-time itself around with them, creating a phenomenon called frame dragging, or the lens-Thirring effect. This frame dragging creates a region called the ergosphere, where space-time itself is pulled around the black hole with such intensity that nothing, not even light, can remain stationary relative to distant observers. Objects in the ergosphere are forced to rotate with the black hole, swept along by the current of space-time itself. Yet remarkably, unlike the event horizon, escape from the ergosphere remains possible, though only in the direction of the black hole's rotation. The study of these regions has revealed something unexpected about the nature of black holes. They're not the simple, featureless objects once imagined. Instead, they're dynamic, complex entities that can store and release enormous amounts of energy. The process of extracting energy from a rotating black hole through the ergosphere, known as the Penrose process, demonstrates that black holes can serve as cosmic batteries, storing rotational energy that can theoretically be harvested. But perhaps the most profound mystery surrounding event horizons concerns their relationship with quantum mechanics. As we've discussed, Hawking radiation suggests that black holes slowly evaporate over time. But this process creates what Stephen Hawking himself called his greatest blunder: the information paradox. If information falling into a black hole is destroyed when the black hole evaporates, it would violate one of the fundamental principles of quantum mechanics, which states that information cannot be destroyed. This paradox has led to some of the most innovative thinking in modern physics. The holographic principle, proposed by Gerard 't Hooft and Leonard Susskind, suggests that all the information contained within a volume of space can be encoded on its boundary. In the context of black holes, this means that all the information that falls past the event horizon might actually be encoded on the horizon itself, like a cosmic hologram. This principle has profound implications for our understanding of reality. If the holographic principle is correct, then the three-dimensional world we experience might itself be a projection of information encoded on a two-dimensional surface. The event horizon becomes not just a boundary around a black hole, but a window into the fundamental nature of space, time, and information itself. Recent developments in quantum gravity have introduced even more exotic possibilities. Some theories suggest that what we perceive as the interior of a black hole might not exist at all. Instead, the event horizon might be a kind of quantum membrane, where information is processed and transformed rather than destroyed. This idea, known as the black hole complementarity principle, suggests that the nature of what happens at the event horizon depends on the perspective of the observer. From the outside, an observer would see matter and energy approach the event horizon, slow down due to gravitational time dilation, and eventually fade away as its light is redshifted beyond detection. But from this external perspective, nothing ever actually crosses the event horizon. Instead, it remains frozen at the boundary, its information preserved in the quantum fluctuations of the horizon itself. Meanwhile, from the perspective of an infouling observer, the journey across the event horizon proceeds normally, at least initially. They would pass through the boundary without noticing anything special, continuing their journey toward the singularity at the center. But quantum mechanics suggest that this observer's experience might be fundamentally different from what classical physics would predict. The firewall hypothesis, proposed by physicists including Joseph Polchinski, suggests that quantum effects near the event horizon might create a wall of high-energy particles that would incinerate anything attempting to cross. This radical idea challenges our understanding of what happens at the event horizon and has sparked intense debate among physicists. These quantum effects arise from the subtle interplay between gravity and quantum mechanics near the event horizon. Virtual particle pairs, which constantly appear and disappear in the quantum vacuum, behave differently in the intense gravitational field of a black hole. Near the event horizon, one particle from each pair might fall into the black hole while the other escapes, creating Hawking radiation. But this process might also create quantum entanglement between the interior and exterior of the black hole, leading to the information paradox. The resolution of these paradoxes continues to drive cutting-edge research in theoretical physics. Some physicists propose that black holes might not have event horizons at all, but rather apparent horizons that can form and dissolve as matter and energy interact with the gravitational field. Others suggest that the interior of black holes might be connected to other regions of spacetime through wormholes, creating a cosmic network of hidden passages. String theory, which attempts to unify quantum mechanics and general relativity, offers its own perspective on event horizons. In string theory, Black holes are described as collections of vibrating strings, and the event horizon emerges as a collective property of these quantum strings. This microscopic description of black holes has led to new insights into their thermodynamic properties and has provided a framework for understanding how information might be preserved even as black holes evaporate. The study of event horizons has also revealed deep connections between gravity, thermodynamics, and information theory. The entropy of a black hole, which measures the amount of information it contains, is proportional to the area of its event horizon rather than its volume. This relationship, known as the Bekenstein-Hawking entropy, suggests that the event horizon acts like a cosmic hard drive, storing information on its surface. This connection between area and entropy has led to new insights into the nature of spacetime itself. Some physicists now believe that spacetime might be an emergent property of quantum entanglement, with the geometry of space and time arising from the complex network of quantum correlations between microscopic degrees of freedom. The event horizon, in this view, represents a boundary where these quantum correlations become so intense that they create the illusion of a geometric barrier. As we continue to study these cosmic boundaries, new questions emerge with each discovery. Are event horizons truly one-way membranes, or do they permit some form of communication or escape? How do quantum effects modify the classical description of black holes? What happens to information that falls past the event horizon? These questions touch on the deepest mysteries of physics and challenge our understanding of the fundamental nature of reality. The answers to these questions might come from unexpected directions. Advances in quantum computing might provide new tools for simulating the quantum effects near event horizons. Gravitational wave detectors might reveal new information about the structure of black holes and their horizons. And future space-based telescopes might provide unprecedented views of matter and energy as they approach and interact with these cosmic boundaries. In the meantime, the event horizon remains one of the most profound and mysterious concepts in modern physics. It represents the boundary between the known and the unknowable, the limit of our ability to observe and understand the universe. Yet it also serves as a gateway to new physics, a laboratory where the most extreme conditions in the universe test our theories and push the boundaries of human knowledge. Tonight, as you drift towards sleep, imagine standing at the edge of the knowable universe, gazing toward an event horizon that marks the boundary between physics and mystery. In that liminal space, where space and time curve beyond recognition, the universe reveals its deepest secrets to those patient enough to listen. The event horizon beckons, not as a destination, but as a doorway to understanding the profound mysteries that lie at the heart of existence itself. Sweet dreams, fellow explorers of the cosmic frontier. The mysteries of the event horizon will continue their eternal dance, waiting for the next generation of curious minds to unlock their secrets and expand our understanding of the magnificent, mysterious universe we call home. The event horizon represents perhaps the most profound boundary in physics, not a physical wall or barrier, but a mathematical point of no return, where the very nature of causality itself breaks down. To understand this invisible threshold, we must first grasp what makes it so fundamentally different from any other boundary we encounter in our daily experience. Picture yourself standing at the edge of a cliff. You can see the drop below, feel the wind, and most importantly, you can step back to safety. The event horizon offers no such luxury. It's a one-way membrane in space-time where the future becomes inexorably linked to the interior of a black hole. Once crossed, every possible path through space and time leads inward, making escape not just difficult or unlikely, but literally impossible according to the laws of physics. The event horizon's location depends entirely on the mass of the black hole that creates it. For a black hole with the mass of our Sun, the event horizon would sit at about 3 kilometers from the center. for the supermassive black hole at the center of our galaxy, containing roughly 4 million solar masses, the event horizon extends to about 12 million kilometers, roughly 17 times the radius of the Sun. This boundary scales directly with mass, following what physicists call the Schwarzschild radius, named after Carl Schwarzschild, who first derived the mathematics describing this phenomenon just months after Einstein published his theory of general relativity. What makes the event horizon truly extraordinary is how it demonstrates the relative nature of reality itself. From the perspective of someone falling toward a black hole, crossing the event horizon might feel surprisingly mundane, at least initially. For stellar mass black holes, the tidal forces would be devastating, stretching you into a thin strand in a process colorfully termed spaghettification. But for supermassive black holes, you could theoretically cross the event horizon and continue falling inward for minutes or even hours before encountering the true singularity at the center. However, to an outside observer watching your journey, something far stranger occurs. As you approach the event horizon, time dilation effects become extreme. Your movements appear to slow down dramatically. Your image becomes increasingly redshifted, and you seem to freeze at the event horizon itself, gradually fading from view as your light is stretched to longer and longer wavelengths. From the outside universe's perspective, you never quite cross the event horizon. You become trapped in a kind of temporal amber, your image preserved but increasingly dim and red. This creates one of the most fascinating paradoxes in physics. Two equally valid descriptions of the same event that seem to contradict each other. You, the infalling observer, experience crossing the event horizon and continuing inward. Yet outside observers see you frozen at the boundary forever. Both perspectives are correct within their own reference frames, illustrating the profound way that gravity warps not just space, but time itself. The event horizon also serves as a perfect laboratory for exploring the intersection of quantum mechanics and general relativity. Stephen Hawking's groundbreaking work showed that black holes aren't perfectly black. They emit radiation due to quantum effects near the event horizon. Virtual particle pairs that constantly pop into existence throughout space can be separated by the intense gravitational field, with one particle falling into the black hole, while the other escapes as Hawking radiation. This process causes black holes to slowly evaporate over time, with smaller black holes radiating away their mass faster than larger ones. This evaporation process leads to the information paradox, one of the most profound puzzles in modern physics. If information that falls into a black hole is destroyed when the black hole evaporates, it would violate a fundamental principle of quantum mechanics that information must be conserved. Various solutions have been proposed, from the idea that information is encoded in the Hawking radiation to more exotic concepts like firewalls at the event horizon or the holographic principle, which suggests that all the information about a black hole's interior might be encoded on its two-dimensional surface. The event horizon also plays a crucial role in our understanding of space-time itself. Near the event horizon, space and time become so warped that the normal rules of causality break down. The event horizon represents the boundary where the escape velocity equals the speed of light, the ultimate speed limit of the universe. Inside this boundary, space itself flows inward faster than light can travel outward, creating an inexorable current that sweeps everything toward the singularity. For rotating black holes, the situation becomes even more complex. The dragging of space-time by the spinning black hole creates an ergosphere, a region outside the event horizon where space-time itself is dragged around the black hole. Within the ergosphere, it becomes impossible to remain stationary relative to distant observers, as you're forced to rotate with the twisted space-time. This frame-dragging effect offers potential mechanisms for extracting energy from rotating black holes. through processes like the Penrose mechanism. The study of event horizons has also revealed deep connections between gravity, thermodynamics, and information theory. Black holes have temperature and entropy, with their entropy proportional to the area of the event horizon, rather than the volume enclosed. This area law for black hole entropy has profound implications for our understanding of how information is stored and processed in the universe, suggesting that the maximum information content of any region of space might be determined by the area of its boundary rather than its volume. Event horizons serve as cosmic laboratories where the most extreme physics in the universe plays out. They represent the ultimate testing ground for our theories about the nature of space, time, matter, and information. As we continue to observe black holes with increasingly sophisticated instruments, from gravitational wave detectors to the Event Horizon Telescope, we're gaining new insights into these mysterious boundaries and the fundamental nature of reality itself. The event horizon stands as perhaps the most perfect example of how the universe operates according to precise mathematical laws, even in the most extreme conditions imaginable. It reminds us that the cosmos is far stranger and more wonderful than our everyday experience suggests, governed by principles that challenge our most basic assumptions about the nature of existence, while revealing the elegant mathematical structure that underlies all of physical reality. Now, we delve into the very fabric of reality itself, where the event horizon reveals its most profound secrets. The boundary we've explored isn't merely a physical barrier, it's a cosmic translator, converting the language of gravity into the vocabulary of quantum mechanics. Here, in this liminal space between the known and unknowable, we encounter phenomena that challenge our deepest assumptions about information, entropy, and the fundamental nature of existence. The event horizon operates as nature's ultimate encryption device. As matter approaches this boundary, its information doesn't simply vanish, it becomes encoded in increasingly subtle ways. The holographic principle suggests that every bit of information falling into a black hole leaves its fingerprint on the event horizon's surface, like shadows cast on a cosmic screen. This encoding process reveals something remarkable. The event horizon acts as a vast library, storing the complete history of everything that has ever crossed its threshold. But this library operates by rules that defy our everyday understanding. The information isn't stored in the way we might imagine, as discrete files or records, but rather as quantum correlations spread across the horizon's entire surface. Each infinitesimal patch of the event horizon contains information about the whole, much like a hologram, where every fragment contains the complete image. This distributed storage system ensures that no single point of failure can erase the accumulated knowledge of billions of years of cosmic history. The thermal properties of the event horizon create an even more intriguing puzzle. Hawking radiation emerges not from within the black hole, but from the quantum foam that surrounds the event horizon. Virtual particle pairs, those ephemeral fluctuations in the vacuum of space, find themselves separated by this cosmic boundary. One particle falls inward while its partner escapes, carrying with it a tiny portion of the black hole's mass energy. This process transforms the event horizon into a quantum radiator, slowly dissolving the very structure that created it. The temperature of this radiation depends inversely on the black hole's mass. Larger black holes radiate more slowly and at lower temperatures than smaller ones. For stellar mass black holes, this temperature is incredibly cold, far below the cosmic microwave background radiation that permeates space. These giants will persist for unimaginably long times, their event horizons serving as nearly eternal boundaries in our universe. But smaller black holes, should they exist, would radiate more intensely, their event horizons shrinking at accelerating rates until they vanish in final bursts of high-energy radiation. This evaporation process creates what physicists call the information paradox. If information that falls into a black hole becomes encoded on the event horizon, what happens to that information when the black hole evaporates completely? The early Hawking radiation appears to be completely thermal, carrying no information about what fell into the black hole. Yet quantum mechanics insists that information cannot be destroyed. This paradox has driven decades of research into the deepest connections between gravity, quantum mechanics, and information theory. Recent theoretical advances suggest that the information paradox may resolve through subtle quantum correlations between early and late Hawking radiation. The event horizon, in this view, acts as a quantum error-correcting code, protecting information even as it appears to be lost. The radiation that emerges carries encrypted information about the black hole's contents, but this information only becomes readable when we can observe the complete evaporation process, a timeline that exceeds the current age of the universe for any realistic black hole. The event horizon also serves as a natural laboratory for studying the emergence of spacetime itself. In the vicinity of the horizon, the usual distinction between space and time becomes fluid. The mathematical description of the event horizon reveals that it's not a fixed boundary, but a dynamic surface that responds to the black hole's rotation, charge, and interaction with its environment. For rotating black holes, this boundary becomes even more complex, with the ergosphere creating a region where space-time itself is dragged around the spinning mass. Within the ergosphere, the event horizon exhibits remarkable properties. Energy can be extracted from the black hole through a process called the Penrose mechanism, where carefully orchestrated trajectories can actually remove rotational energy from the black hole while allowing the extracted energy to escape to infinity. This process reveals that the event horizon is not merely a one-way valve, but a dynamic interface capable of complex energy exchanges with the outside universe. The quantum geometry of the event horizon suggests that space and time themselves may be emergent properties of more fundamental quantum information. The horizon area, measured in Planck units, corresponds exactly to the number of quantum bits needed to encode all the information contained within the black hole. This correspondence hints at a deeper truth, that spacetime itself may be woven from quantum information, with the event horizon serving as a visible manifestation of this deeper informational structure. The event horizon also provides insights into the nature of consciousness and observation. The boundary appears different depending on the observer's reference frame. A distant observer never sees anything cross the event horizon, watching instead as infalling matter redshifts and fades away. But for the infalling observer, the crossing occurs at a definite moment, with nothing particularly special marking the transition. This observer-dependent nature of the event horizon raises profound questions about the role of consciousness in physics and the relationship between subjective experience and objective reality. These quantum properties of the event horizon connect to broader questions about the nature of time itself. Near the horizon, time dilation becomes extreme, with time appearing to slow down and eventually stop for distant observers. Yet this temporal distortion doesn't represent a failure of physics, but rather reveals the deep connection between gravity and the flow of time. The event horizon serves as a cosmic chronometer, marking the boundary where time's arrow becomes fundamentally altered by the curvature of space-time. As we probe deeper into these quantum mysteries, the event horizon reveals itself as far more than a simple boundary. It's a cosmic interface where the classical world of general relativity meets the quantum realm of uncertainty and probability. Here, in this liminal space, we glimpse the future of physics, a unified theory that will eventually reconcile gravity with quantum mechanics and reveal the true nature of reality itself. The event horizon stands as a testament to the profound mysteries that still await us in the cosmos. It reminds us that the universe operates by rules far stranger and more beautiful than our everyday experience suggests, and that the boundaries we perceive often mark the beginning of even greater mysteries rather than their end. Looking at where we left off in our exploration of the event horizon, we now delve into one of the most profound mysteries that emerges from our understanding of these cosmic boundaries. The event horizon isn't just a simple barrier around a black hole. It's a gateway to understanding the very nature of information itself and how it behaves in the universe. Consider this fascinating puzzle that has kept physicists awake at night for decades. When matter falls into a black hole, it carries with it information about its quantum state, its history, its very identity. This information describes everything about that matter, from the spin of its electrons to the arrangement of its atoms. According to our understanding of quantum mechanics, information cannot simply vanish from the universe. It must be preserved somewhere, somehow. This principle, known as unitarity, is one of the fundamental pillars of quantum theory. Yet black holes present us with what appears to be a direct contradiction to this principle. As matter crosses the event horizon, it seems to disappear forever into the singularity at the black hole's center. From our perspective outside the event horizon, this information appears to be lost permanently. But quantum mechanics tells us this cannot be. The information must be preserved. But where does it go? This is the heart of the black hole information paradox, a puzzle that has driven some of the most brilliant minds in physics to develop radical new theories about the nature of reality itself. Stephen Hawking's discovery of black hole radiation added another layer to this mystery. If black holes evaporate by emitting radiation, and if this radiation is completely random and thermal as originally proposed, then any information that fell into the black hole would be destroyed when the black hole finally evaporates completely. This would violate the fundamental principle that information is conserved in quantum mechanics. The universe would essentially be deleting information, something that should be impossible according to our best theories. But perhaps the most startling resolution to this paradox comes from reconsidering what actually happens at the event horizon itself. Some physicists now propose that the event horizon isn't the smooth, empty boundary that Einstein's equations suggest. Instead, it might be a roiling wall of high-energy particles, a cosmic firewall that incinerates anything attempting to cross it. This firewall would prevent information from ever actually entering the black hole, preserving the principle of information conservation, but at the cost of another cherished principle, the equivalence principle that says falling through space should feel no different from floating freely. The implications of this firewall hypothesis are staggering. It suggests that the smooth spacetime predicted by general relativity breaks down at the event horizon, replaced by something far more violent and chaotic. An astronaut approaching a black hole wouldn't experience the gentle fall into darkness that relativity predicts. Instead, they would encounter a wall of destruction that would vaporize them instantly upon reaching the horizon. The black hole becomes not a gateway to another realm, but a cosmic incinerator that destroys anything that dares approach too closely. Yet another possibility emerges from the strange world of quantum entanglement. Perhaps the information that falls into a black hole doesn't disappear at all, but becomes encoded in the Hawking radiation itself through subtle quantum correlations. As the black hole evaporates, it gradually releases this information back into the universe, but in such a scrambled form that it would take longer than the age of the universe to decode. The information is preserved, but in a form so thoroughly mixed that it's practically irretrievable. This leads us to one of the most mind-bending concepts in modern physics, the holographic principle. This idea suggests that all the information contained within a volume of space can be encoded on its boundary. Applied to black holes, this means that everything that falls past the event horizon isn't really inside the black hole at all. Instead, it's encoded as information on the surface of the event horizon itself, like a cosmic hologram projected onto the black hole's boundary. The holographic principle implies something profound about the nature of reality itself. It suggests that what we perceive as three-dimensional space might actually be an illusion, a projection of information stored on a two-dimensional surface. The event horizon becomes not just a boundary in space, but a boundary between different ways of describing reality. From outside the black hole, we can describe everything in terms of information encoded on the horizon surface. From inside, assuming one could somehow survive the journey, reality might be described in terms of the familiar three-dimensional space we experience daily. This duality of description extends to the very foundations of how we understand space and time. The event horizon represents a place where different observers literally experience different realities. An outside observer sees matter slow down and freeze at the horizon, its information encoded forever on the surface. An infalling observer experiences crossing the horizon and continuing toward the singularity, carrying their information with them. Both descriptions are valid within their respective frameworks, yet they seem to describe completely different physical situations. The resolution of this paradox may require us to abandon some of our most basic assumptions about the nature of space-time itself. Some physicists propose that space-time is not fundamental but emergent, arising from more basic quantum information processing. In this view, the event horizon becomes a place where this emergence breaks down, where the illusion of continuous space-time gives way to the underlying quantum mechanical reality. String theory, our most ambitious attempt to unify quantum mechanics and general relativity, offers its own unique perspective on the information paradox. In string theory, the fundamental constituents of reality are not particles, but tiny vibrating strings. These strings exist in a space with more dimensions than the three we experience, and black holes in string theory can be described as complex configurations of these higher dimensional strings. The information that falls into a string theory black hole doesn't disappear, but becomes encoded in the string configurations themselves, providing a natural mechanism for information preservation. But perhaps the most radical solution to the information paradox comes from questioning whether the paradox exists at all. Some physicists argue that the very notion of information crossing the event horizon is meaningless because from the perspective of any outside observer, this crossing never actually occurs. Matter approaching the horizon slows down and redshifts until it becomes effectively frozen at the boundary. From this perspective, nothing ever truly enters the black hole, and the information paradox dissolves because no information is ever actually lost. This resolution, however, raises its own puzzles. If nothing ever crosses the event horizon, how do black holes grow? How do they merge with other black holes? How do they eventually evaporate through Hawking radiation? The answers to these questions require us to think carefully about the relationship between different reference frames and how physical processes appear different to different observers. The study of the information paradox has led to remarkable advances in our understanding of quantum gravity, the long-sought theory that would unify quantum mechanics and general relativity. It has revealed deep connections between seemingly unrelated areas of physics, from quantum field theory to thermodynamics to information theory. The event horizon, once thought to be a relatively simple boundary, has become a window into the most fundamental aspects of physical reality. As we continue to probe the mysteries of the event horizon, we find ourselves confronting questions that go to the very heart of what it means to exist in a quantum universe. Does information have a physical reality independent of the matter that carries it? Can space and time themselves emerge from more fundamental quantum processes? Is the three-dimensional world we experience actually a projection of information stored on distant boundaries? These questions push us to the limits of human understanding, forcing us to reconsider our most basic assumptions about the nature of reality. The event horizon, that seemingly simple boundary around a black hole, has become a laboratory for exploring the deepest mysteries of existence itself. It challenges us to think beyond the familiar concepts of space and time, matter and energy, and to consider the possibility that reality at its most fundamental level might be stranger and more wonderful than we ever imagined. The journey to understand the event horizon and its information paradox continues, driving new discoveries and challenging our understanding of the universe. Each new insight reveals additional layers of complexity, suggesting that the true nature of these cosmic boundaries may be even more profound than we currently comprehend. In our quest to understand the event horizon, we are not just studying black holes, but probing the very foundations of physical reality itself. The event horizon represents far more than just a boundary. It's a gateway to understanding the fundamental nature of reality itself. As we've journeyed through the mysteries of black holes, we've discovered that these cosmic phenomena challenge our most basic assumptions about space, time, and the very fabric of existence. What makes the event horizon truly extraordinary is how it serves as a testing ground for our deepest theories about the universe. Here, at this invisible threshold, general relativity meets quantum mechanics in ways that continue to perplex and inspire physicists. The event horizon doesn't just mark where light cannot escape. It marks where our understanding of physics itself begins to transform. Consider the profound implications of what we've explored together. The information paradox suggests that quantum information might be preserved in ways we're only beginning to comprehend. The holographic principle hints that all the information about a three-dimensional black hole might be encoded on its two-dimensional surface. These aren't merely abstract mathematical concepts, they're clues to the deepest workings of reality. The event horizon also reveals the intimate connection between gravity, thermodynamics, and information theory. Black holes have temperature, they emit radiation, and they evolve over cosmic timescales. This connection between seemingly disparate fields of physics suggests that the universe operates on principles far more unified and elegant than we might have imagined. Perhaps most remarkably, the event horizon challenges our perception of time itself. While distant observers see time dilate to a crawl near the boundary, the infalling observer experiences something entirely different. This dual nature of reality, where the same event can be perceived so differently depending on one's reference frame, speaks to the malleable nature of space-time itself. The study of event horizons has also opened new avenues for understanding the early universe, the nature of dark matter and dark energy, and the ultimate fate of cosmic structures. These boundaries that seem so exotic and remote actually connect to the largest questions about our cosmic origins and destiny. As we continue to probe these mysteries through gravitational wave detectors, advanced telescopes, and theoretical breakthroughs, we're discovering that the event horizon isn't just a feature of black holes, it's a window into the deepest structures of reality. Each new discovery reveals how these invisible boundaries continue to reshape our understanding of what it means to exist in a universe where space and time themselves can be warped, stretched, and transformed. The event horizon reminds us that in the cosmos, the most profound truths often lie hidden behind veils of mystery, waiting for curious minds to peer deeper into the darkness and discover the light of understanding that illuminates the very foundations of existence itself. We've journeyed through the fundamental physics, the mathematical descriptions, the observational evidence, and the theoretical frameworks. Now, as we approach the conclusion of our cosmic odyssey, we turn to perhaps the most profound aspect of the event horizon, its role as a natural laboratory for testing the very limits of our understanding. The event horizon stands as more than just a boundary in spacetime. It represents the frontier where our most cherished theories converge and sometimes clash, where the smooth predictions of general relativity meet the quantum mechanical reality of the microscopic world. This convergence has driven physicists to develop new frameworks, new ways of thinking about reality itself. Consider the holographic principle, which suggests that all the information contained within a volume of space can be encoded on its boundary. The event horizon becomes not just a point of no return, but a cosmic hard drive, storing information about everything that has ever fallen into the black hole. This principle has revolutionized our understanding of how information is processed and stored in the universe, suggesting that reality itself might be fundamentally two-dimensional, with our three-dimensional experience being a kind of holographic projection. The study of event horizons has also led to profound insights about the nature of spacetime itself. Near the event horizon, spacetime becomes so warped that time and space begin to interchange roles. Inside the event horizon, moving toward the singularity becomes as inevitable as moving forward in time outside the horizon. This geometric inevitability reveals something deep about the fabric of reality, about how matter and energy sculpt the very stage upon which cosmic drama unfolds. Perhaps most remarkably, the event horizon has taught us about the deep connections between gravity, thermodynamics, and information theory. The discovery that black holes have temperature and entropy, that they can evaporate through Hawking radiation, has forged links between previously disconnected areas of physics. The entropy of a black hole is proportional to the area of its event horizon, not its volume, suggesting that the fundamental degrees of freedom in any region of space are encoded on its boundary. This boundary-based encoding has implications that extend far beyond black holes. It suggests that the universe itself might be holographic, that the information describing everything within our cosmic horizon might be encoded on that distant boundary. As we peer deeper into space and further back in time, we're not just observing distant galaxies, but potentially reading the cosmic information encoded on the boundary of our observable universe. The event horizon also serves as a natural laboratory for testing theories of quantum gravity. The extreme conditions near the horizon, where space-time curvature becomes enormous and quantum effects become significant, provide a testing ground for our attempts to unify general relativity with quantum mechanics. While we cannot yet create such conditions in terrestrial laboratories, the universe has provided us with these natural experiments in the form of black holes and their event horizons. The firewall paradox, which we explored earlier, represents the cutting edge of this research. It forces us to question fundamental assumptions about the nature of spacetime, about whether the equivalence principle holds in all circumstances, about how information is preserved in quantum systems. The resolution of this paradox may require us to abandon some of our most basic assumptions about reality, to develop new mathematical frameworks that can accommodate both the smooth geometry of general relativity and the discrete, probabilistic nature of quantum mechanics. As we stand on the threshold of a new era in physics, with gravitational wave detectors allowing us to probe the dynamics of spacetime directly, with the Event Horizon Telescope providing us with actual images of event horizons, we are witnessing the transition from theoretical speculation to direct observation. The event horizon, once a purely mathematical concept, has become a physical reality that we can study, measure, and photograph. The implications extend beyond physics into philosophy and our understanding of reality itself. The event horizon challenges our notions of causality, of the flow of time, of the nature of information, and its conservation. It forces us to confront the possibility that space and time are not fundamental but emergent properties of something more basic, something that might be described in terms of information, entanglement, or geometric relationships that we are only beginning to understand. In the coming decades, as our observational capabilities continue to improve and our theoretical understanding deepens, the event horizon will undoubtedly continue to serve as a beacon, guiding us toward a more complete understanding of the universe. It represents not just a boundary in space, but a boundary in our knowledge, a horizon beyond which new discoveries await. The event horizon teaches us that the universe is far stranger and more wonderful than we ever imagined. It reminds us that at the deepest level, reality is not just about matter and energy, but about information, about the ways in which the universe processes and stores the record of its own evolution. As we continue to probe these cosmic boundaries, we are not just studying distant objects in space, but exploring the fundamental nature of existence itself. The journey through the physics of event horizons reveals the beautiful interconnectedness of all physical phenomena, from the quantum realm to the cosmic scale. It shows us that the universe is not a collection of separate objects and forces, but a unified whole, where geometry and physics, information and reality, space and time are all aspects of a single, magnificent tapestry that we are privileged to study and slowly begin to understand. As we've journeyed through the depths of black holes and witnessed the universe's most extreme gravitational phenomena, we find ourselves at the threshold of understanding one of physics' most profound mysteries, the event horizon itself. This invisible boundary represents not just the point of no return for matter and energy, but the very edge of what we can observe and comprehend about the universe's fundamental nature. The event horizon emerges from the elegant mathematics of general relativity, where Einstein's equations reveal that sufficiently massive objects can curve space-time so severely that not even light can escape. It's a boundary that exists not in ordinary space, but in the four-dimensional fabric of space-time itself. Picture, if you will, a cosmic whirlpool where the current of space-time flows faster than the speed of light, creating a region forever cut off from the rest of the universe. What makes the event horizon so fascinating is its dual nature. To an outside observer, it appears as a dark sphere marking the boundary of the black hole, a surface where time itself seems to slow to a crawl. Light from objects approaching the horizon becomes increasingly redshifted, stretched to longer and longer wavelengths until it fades into invisibility. The horizon appears frozen in time, preserving the last moments of anything that falls toward it in an eternal tableau. Yet, for someone crossing the event horizon, the experience would be profoundly different. From their perspective, nothing special happens at the moment of crossing. They would pass through this invisible boundary as if it were empty space, unaware that they had just crossed the ultimate point of no return. The horizon is what physicists call a local phenomenon, its effects only becoming apparent when viewed from the broader context of space-time. The mathematics describing the event horizon reveal its intimate connection to the black hole's mass. The Schwarzschild radius, named after Carl Schwarzschild, who derived the solution to Einstein's equations just months after their publication, defines the size of this boundary. For a black hole with the mass of our Sun, the event horizon would have a radius of about 3 kilometers. Double the mass, and the horizon radius doubles as well. This linear relationship between mass and horizon size means that supermassive black holes, containing millions or billions of solar masses, possess event horizons that could engulf entire planetary systems. But the event horizon is not merely a theoretical construct. It represents a fundamental limit to observation and information transfer in our universe. Beyond this boundary, the normal rules of causality break down. Signals sent from within the horizon can never reach the outside world, creating what physicists call a causal disconnect. This has profound implications for our understanding of information and entropy in the universe. The horizon also serves as a natural laboratory for testing the most extreme predictions of general relativity. Near the event horizon, space-time curvature becomes so severe that tidal forces can stretch objects into long, thin shapes in a process colorfully termed spaghettification. These tidal effects arise because gravity becomes significantly stronger at one end of an object than the other, creating forces that can overcome the electromagnetic bonds holding matter together. Perhaps most intriguingly, the event horizon plays a central role in Stephen Hawking's revolutionary discovery that black holes emit radiation. Through the lens of quantum mechanics, the vacuum of space near the horizon becomes a seething cauldron of virtual particle pairs. Normally, these pairs annihilate each other almost instantly, but the extreme curvature of space-time near the horizon can separate them, with one particle falling into the black hole while the other escapes as real radiation. This Hawking radiation carries energy away from the black hole, causing it to slowly evaporate over time. The process is extraordinarily slow for stellar mass black holes, taking longer than the current age of the universe to evaporate completely. But for microscopic black holes, if they exist, the evaporation would be rapid and explosive. The event horizon thus becomes not just a boundary of space, but a boundary in time, marking the eventual fate of every black hole in the universe. The discovery of Hawking radiation has led to one of physics' most perplexing puzzles: the information paradox. If information falling into a black hole is truly lost when the black hole evaporates, it would violate one of the fundamental principles of quantum mechanics. This has sparked decades of theoretical work attempting to resolve the paradox, with proposals ranging from information being encoded on the horizon's surface to the idea that the horizon itself is not a smooth boundary, but a seething firewall of high-energy particles. Recent developments in theoretical physics have suggested that the event horizon might be understood through the lens of holography, where all the information about the black hole's interior is encoded on its two-dimensional surface. This holographic principle suggests that the three-dimensional physics we observe might be a projection of more fundamental two-dimensional dynamics occurring at the horizon. The study of event horizons has also revealed deep connections between gravity, thermodynamics, and information theory. The horizon area is directly related to the black hole's entropy, with each bit of information corresponding to a specific area on the horizon's surface. This relationship suggests that space itself might be granular at the smaller scales, composed of discrete units of area and volume. Modern observations have brought us tantalizingly close to directly imaging event horizons. The Event Horizon Telescope, a global network of radio telescopes, has captured images of the glowing material surrounding supermassive black holes, revealing the shadow cast by their event horizons. These observations provide direct confirmation of Einstein's predictions and offer new ways to test our understanding of these extreme objects. The event horizon also plays a crucial role in the formation and evolution of galaxies. Supermassive black holes at galactic centers regulate star formation through their gravitational influence and the energy released by material falling toward their horizons. The interplay between black hole growth and galaxy evolution has shaped the cosmic landscape we observe today. As we peer deeper into the nature of event horizons, we find ourselves confronting fundamental questions about the nature of reality itself. Do black holes destroy information, or do they preserve it in some form we don't yet understand? Is the horizon a real physical boundary, or an emergent phenomenon arising from more fundamental physics? These questions push us to the very limits of our current understanding and hint at new physics waiting to be discovered. The event horizon stands as a testament to the power of mathematical physics to predict phenomena far beyond our everyday experience. From Einstein's elegant equations emerged the prediction of these invisible boundaries, confirmed decades later through increasingly sophisticated observations. They remind us that the universe is far stranger and more wonderful than our intuition suggests, filled with phenomena that challenge our deepest assumptions about space, time, and the nature of existence itself. As we continue to probe these cosmic mysteries, the event horizon remains one of physics' most compelling frontiers. It represents not just the boundary of black holes, but the boundary of our knowledge, marking the edge of what we can observe and understand about the universe. In studying these invisible barriers, we gain insights into the fundamental structure of reality and our place within the cosmic tapestry. As we stand at the precipice of understanding these cosmic boundaries, the event horizon continues to challenge our most fundamental assumptions about reality itself. The implications of what we've discovered extend far beyond the realm of theoretical physics, touching upon the very nature of existence, information, and the structure of space-time. The event horizon represents more than just a boundary around a black hole. It embodies the intersection of our most successful theories of physics. When we observe the intricate dance between general relativity and quantum mechanics at these cosmic edges, we witness the universe revealing its deepest secrets. The horizon serves as a natural laboratory where the extreme conditions force us to confront the limitations of our current understanding and push the boundaries of human knowledge. One of the most profound realizations emerging from our study of event horizons is how they reshape our understanding of information itself. The information paradox, which we've explored extensively, isn't merely an abstract puzzle for theoretical physicists to solve. It represents a fundamental crisis in our understanding of how information behaves in the universe. If information can truly be destroyed, as classical black hole evaporation might suggest, then the very foundations of quantum mechanics would crumble. Yet if information is preserved, as quantum mechanics demands, then our understanding of space-time and causality must undergo radical revision. The holographic principle, born from the study of event horizons, has revolutionized our conception of reality. The idea that all the information contained within a volume of space can be encoded on its boundary surface suggests that what we perceive as three-dimensional reality might be nothing more than a projection from a two-dimensional surface. This isn't science fiction. It's a serious theoretical framework that has found applications across physics, from condensed matter systems to cosmology itself. The event horizon taught us that the universe might be far stranger and more interconnected than we ever imagined. As we've seen, the mathematics of event horizons reveals the deep connection between gravity, thermodynamics, and information theory. Black holes have temperature, entropy, and follow the laws of thermodynamics in ways that initially seemed impossible. This connection has led to profound insights about the nature of space-time itself. The Bekenstein-Hawking entropy formula, which relates a black hole's entropy to the area of its event horizon, suggests that space-time might be emergent rather than fundamental. Perhaps the smooth fabric of Einstein's space-time is actually woven from more fundamental quantum information, with the event horizon serving as the interface where this hidden structure becomes visible. The technological achievements that have allowed us to directly observe event horizons represent one of humanity's greatest scientific accomplishments. The event horizon. Telescopes' images of the supermassive black holes in M87 and our own Sagittarius A-AS have transformed event horizons from mathematical abstractions into observable phenomena. These images don't just confirm Einstein's predictions, they open entirely new avenues for exploring the universe. Future improvements in observational technology will allow us to study the dynamic behavior of matter and energy near event horizons in unprecedented detail, potentially revealing new physics that our current theories cannot predict. The study of event horizons has also illuminated the concept of cosmic censorship, the idea that singularities are always hidden behind event horizons. This principle, if true, protects the universe from the mathematical pathologies that arise when general relativity breaks down. Yet recent theoretical work suggests that cosmic censorship might not be absolute, and under certain extreme conditions, naked singularities might be possible. If such objects exist, they would represent regions where the laws of physics as we know them simply cease to apply, creating windows into realms of reality that lie beyond our current understanding. Event horizons have taught us about the relativity of observation itself. What appears as a point of no return to an outside observer represents a completely different experience for someone crossing the horizon. This fundamental observer dependence challenges our intuitive notions of objective reality and suggests that the universe might be far more subjective than we typically assume. The horizon exists differently for different observers, reminding us that reality itself might be more malleable and perspective-dependent than classical physics would suggest. The connection between event horizons and the arrow of time represents another frontier of understanding. Black holes seem to embody the irreversible flow of time, with their event horizons marking regions where the future is inexorably determined. Yet the microscopic reversibility of quantum mechanics suggests that this irreversibility might be an illusion emerging from our limited perspective rather than representing a fundamental feature of reality. The resolution of this tension might require us to completely reconceptualize our understanding of time itself. As we look toward the future, event horizons continue to drive theoretical innovation. The development of quantum gravity theories, whether through string theory, loop quantum gravity, or other approaches, is fundamentally motivated by the need to understand what happens at and beyond event horizons. These theories might reveal that event horizons are not the impenetrable barriers they appear to be, but rather complex quantum interfaces where information is processed and transformed in ways we cannot yet comprehend. The implications of event horizon physics extend to cosmology itself. If the universe began with a Big Bang, then the entire observable universe might have emerged from conditions similar to those found at black hole event horizons. Understanding these cosmic boundaries might therefore be essential for understanding the origin and ultimate fate of the universe itself. Some theories suggest that our universe might even exist inside a black hole, with our cosmic horizon playing a role analogous to an event horizon. The study of event horizons has also revealed deep connections between physics and information theory that continue to reshape both fields. The realization that black holes behave like quantum computers, processing information in ways that preserve quantum coherence while appearing to destroy it, has led to new insights about the nature of computation itself. These discoveries might eventually lead to new technologies that harness the quantum properties of spacetime, though such applications remain highly speculative. Event horizons challenge our understanding of causality in profound ways. The fact that events beyond the horizon cannot influence the outside universe suggests that causality might be more complex than simple cause and effect relationships. The study of closed time-like curves, wormholes, and other exotic space-time geometries associated with event horizons reveals that time travel and causality violations might be possible under certain extreme conditions, though nature seems to have built-in mechanisms to prevent paradoxes. The philosophical implications of event horizon physics are equally profound. If information is truly fundamental, as suggested by the holographic principle and the information paradox, then consciousness itself might be understood as a pattern of information processing. The event horizon, as the ultimate boundary of information flow, might therefore represent not just a physical boundary, but a fundamental limit on consciousness and observation. This perspective suggests deep connections between physics and the nature of mind that we are only beginning to explore. Recent developments in quantum error correction have revealed surprising connections to event horizon physics. The way quantum computers preserve information despite environmental interference mirrors the way event horizons might preserve information despite the apparent destruction of infalling matter. These connections suggest that event horizons might be understood as natural quantum error-correcting systems, preserving the coherence of quantum information even under the most extreme conditions. The study of event horizons has also revealed the importance of entanglement in the structure of space-time itself. The Einstein-Rosen bridges that connect black holes to their quantum entangled partners suggest that entanglement might be the fundamental mechanism by which space-time is constructed. If this is true, then event horizons represent not just boundaries in space, but nodes in a vast network of quantum correlations that underlies all of reality. As we continue to probe the mysteries of event horizons, we find ourselves confronting questions that challenge the very foundations of scientific inquiry. How can we study regions of space-time that are fundamentally inaccessible to observation? How do we reconcile the apparently contradictory demands of general relativity and quantum mechanics? These questions push us to develop new methodologies and conceptual frameworks that might eventually revolutionize our understanding of science itself. The technological challenges of studying event horizons continue to drive innovation in observational astronomy and theoretical physics. Future space-based telescopes with unprecedented resolution might allow us to observe the dynamic behavior of event horizons in real time, watching as matter and energy cross these cosmic boundaries. Such observations could provide the first direct tests of quantum gravity theories and potentially reveal new physics beyond our current understanding. The mathematical beauty of event horizon physics continues to inspire new theoretical developments. The elegant equations that describe these cosmic boundaries reveal deep symmetries and connections that seem to hint at even more fundamental principles. The study of event horizons has led to the development of new mathematical techniques that have found applications throughout physics and beyond, demonstrating the unexpected unity of mathematical truth. Event horizons also serve as natural laboratories for studying the limits of physical law. The extreme conditions near these boundaries push matter and energy to their absolute limits, creating states that cannot be replicated in terrestrial laboratories. By studying these extreme environments, we gain insights into the fundamental nature of matter, energy, and space-time that would be impossible to obtain otherwise. The connection between event horizons and the fundamental constants of nature reveals another layer of mystery. The precise values of constants, like the speed of light, Planck's constant, and Newton's gravitational constant, determine the properties of event horizons throughout the universe. If these constants were slightly different, event horizons might not exist at all, or they might behave in radically different ways. This observation raises profound questions about why the universe is structured in a way that allows for the existence of these remarkable boundaries. As we contemplate the future of event horizon research, we must acknowledge that our current understanding represents only the beginning of a much longer journey. The questions we've raised about information, causality, and the nature of reality will likely require generations of scientists to fully explore, yet the progress we've made in understanding these cosmic boundaries demonstrates the power of human curiosity and ingenuity to unlock the universe's deepest secrets. The event horizon stands as perhaps the most profound boundary in the universe, separating the known from the unknowable, the observable from the hidden. It represents both a limit to our knowledge and a gateway to new understanding. As we continue to study these remarkable features of space-time, we edge closer to answering some of the most fundamental questions about existence itself. In our exploration of event horizons, we have discovered that the universe is far stranger, more interconnected, and more beautiful than we ever imagined. These cosmic boundaries have taught us that reality itself might be holographic, that information might be more fundamental than matter and energy, and that the nature of space and time might be far more subtle than our everyday experience suggests. The event horizon reminds us that the universe still holds countless mysteries waiting to be discovered. As we stand on the threshold of new technological capabilities and theoretical insights, we can only imagine what new revelations await us. The boundary that once seemed to mark the end of physics has instead become the doorway to entirely new realms of understanding. Perhaps most remarkably, the study of event horizons has shown us that the most extreme and exotic phenomena in the universe are governed by the same fundamental principles that operate in our everyday world. The laws of physics that describe the behavior of event horizons are the same laws that govern the atoms in our bodies and the light from distant stars. This unity suggests that by understanding these cosmic boundaries, we are not just learning about black holes, but about the fundamental nature of reality itself. As we stand at the precipice of our current understanding, the event horizon continues to challenge our most fundamental assumptions about reality itself. What began as a mathematical curiosity in Einstein's equations has evolved into one of the most profound concepts in modern physics, serving as a bridge between the quantum world and the cosmic scale. The horizon represents more than just a boundary around black holes. It embodies the very limits of what we can know and observe about our universe. The journey through our understanding of event horizons reveals the intricate dance between theory and observation that defines modern astrophysics. When Carl Schwarzschild first derived his solution to Einstein's field equations in 1916, he could hardly have imagined that this mathematical construct would become a cornerstone of our understanding of spacetime. The Schwarzschild radius, that critical distance where the escape velocity equals the speed of light, seemed like an abstract mathematical concept. Yet today, we have directly observed the shadows cast by these horizons, transforming theoretical predictions into observable reality. The Event Horizon Telescope's historic images of the supermassive black holes in M87 and our own galactic center have provided unprecedented validation of general relativity's predictions. These observations represent the culmination of decades of theoretical development and technological advancement. The ring of light surrounding the dark shadow in these images is not merely a photograph of a black hole. It is a direct observation of space-time geometry itself, bent and twisted by extreme gravity into configurations that challenge our everyday understanding of space and time. But perhaps the most remarkable aspect of event horizons is how they have forced us to confront the fundamental nature of information and reality. The black hole. Information paradox stands as one of the most significant challenges to our understanding of physics, precisely because it sits at the intersection of quantum mechanics and general relativity. The paradox forces us to question whether information can truly be destroyed, whether the principles of quantum mechanics are universal, and whether our understanding of space-time is complete. Stephen Hawking's discovery of black hole radiation revolutionized our understanding of these objects, transforming them from perfect absorbers into dynamic systems that emit energy and eventually evaporate. The temperature of this radiation, inversely proportional to the black hole's mass, creates a fascinating thermodynamic picture where the largest black holes are the coldest objects in the universe. This connection between gravity and thermodynamics, formalized in the laws of black hole mechanics, suggests deep relationships between seemingly disparate areas of physics. The holographic principle, emerging from our study of black holes, has profound implications that extend far beyond event horizons themselves. If the information content of a volume of space can be encoded on its boundary, this suggests that our three-dimensional reality might be fundamentally different from what we perceive. The holographic principle implies that the universe itself might be a kind of hologram, with all the information about its interior encoded on a distant boundary. This radical reinterpretation of reality emerged directly from attempts to resolve the information paradox. Quantum entanglement has emerged as a crucial player in our understanding of event horizons, offering potential solutions to long-standing paradoxes while raising new questions about the nature of spacetime itself. The idea that entangled particles separated by vast distances can maintain instantaneous correlations challenges our classical notions of locality and causality. When applied to black holes, entanglement suggests that the interior and exterior of a black hole might be connected in ways that transcend the apparent barrier of the event horizon. The firewall paradox represents the cutting edge of current theoretical debates, forcing us to choose between cherished principles of physics. Either the equivalence principle fails at the horizon, creating a wall of high-energy particles, or our understanding of quantum mechanics is incomplete. This paradox illustrates how event horizons continue to serve as testing grounds for our most fundamental theories, pushing the boundaries of what we think we know about the universe. String theory's approach to black holes has provided new mathematical tools for understanding these objects, particularly through the ADS-CFT correspondence. This relationship between theories of gravity in the bulk of spacetime and quantum field theories on the boundary has offered new perspectives on the information paradox and the nature of spacetime itself. The correspondence suggests that gravity and quantum field theory might be different descriptions of the same underlying reality, with the event horizon playing a crucial role in this duality. The study of primordial black holes has opened new avenues for understanding the early universe and the nature of dark matter. These hypothetical objects, formed from density fluctuations in the early universe rather than stellar collapse, could provide insights into conditions shortly after the Big Bang. Their event horizons would encode information about the universe's infancy, making them potential time capsules of cosmic history. Rotating black holes, described by the Kerr metric, have added complexity and richness to our understanding of event horizons. The ergosphere, the region outside the event horizon where spacetime is dragged along with the black hole's rotation, demonstrates how extreme gravity can blur the boundaries between space and time. The possibility of extracting energy from rotating black holes through the Penrose process shows how these objects might serve as cosmic engines, powering some of the most energetic phenomena in the universe. The study of charged black holes, though likely rare in nature, has provided important theoretical insights into the relationship between different types of horizons. The Reissner-Nordstrom solution describes black holes with electric charge, introducing inner and outer horizons that create complex causal structures. These solutions, while probably not realized in nature due to the neutralizing effects of surrounding matter, provide important test cases for our understanding of general relativity and quantum field theory in curved spacetime. The connection between event horizons and thermodynamics has revealed universal principles that apply far beyond black holes themselves. The holographic bound, which limits the amount of information that can be contained in any region of space, emerges from black hole physics, but has implications for information theory, quantum computation, and our understanding of the universe's ultimate limits. The fact that entropy scales with area rather than volume in the presence of gravity suggests fundamental revisions to our understanding of statistical mechanics and thermodynamics. Future observations promise to deepen our understanding of event horizons and test our theoretical predictions with unprecedented precision. Next-generation telescopes and interferometers will provide higher-resolution images of black hole shadows, potentially revealing details of the space-time structure near the horizon. Gravitational wave detectors continue to improve in sensitivity, offering new ways to study black holes and test general relativity in the strong field regime. The search for quantum gravity theories continues to be driven largely by the puzzles presented by event horizons. Loop quantum gravity, causal dynamical triangulation, and other approaches to quantum gravity all must grapple with the lessons learned from black hole physics. The resolution of the information paradox and the nature of space-time at the Planck scale remain central goals of theoretical physics, with event horizons serving as crucial testing grounds for new ideas. The philosophical implications of event horizons extend beyond physics into questions about the nature of reality, causality, and information. The horizon represents an absolute boundary to observation, raising questions about whether science can ever provide a complete description of reality. If information can be preserved in ways that transcend the apparent barrier of the event horizon, this suggests that our classical notions of cause and effect might be fundamentally incomplete. The study of analog black holes in laboratory settings has provided new ways to test our understanding of horizon physics. By creating acoustic or optical analogues of event horizons, researchers can study Hawking radiation and other quantum effects in controlled environments. These experiments bridge the gap between theory and observation, offering insights into phenomena that would be impossible to observe directly at astrophysical black holes. The role of event horizons in cosmology continues to evolve as we develop better understanding of dark energy and the universe's accelerating expansion. The cosmological event horizon, beyond which events become forever unobservable due to cosmic expansion, shares many features with black hole event horizons. The study of these different types of horizons provides insights into the global structure of spacetime and the ultimate fate of the universe. As we look toward the future, event horizons will undoubtedly continue to challenge our understanding and drive new discoveries. The development of quantum computers might provide new tools for simulating black hole physics and testing theories of quantum gravity. Advances in gravitational wave astronomy will open new windows into the strong field regime of general relativity, potentially revealing new aspects of horizon physics. The interdisciplinary nature of event horizon research has led to unexpected connections between seemingly unrelated fields. Concepts from black hole physics have found applications in condensed matter physics, quantum information theory, and even computer science. The holographic principle has inspired new approaches to understanding complex systems, while entanglement entropy has become a crucial tool in quantum many-body physics. The study of event horizons has also revealed the importance of observer dependence in physics. The fact that different observers can disagree about fundamental aspects of reality, such as whether an event horizon exists or whether information has been destroyed, challenges our classical notions of objective reality. This observer dependence suggests that the universe might be fundamentally more complex and subtle than our everyday experience suggests. The mathematical structures underlying event horizons have revealed deep connections between geometry, topology, and physics. The causal structure of spacetime near horizons involves sophisticated mathematical concepts that have applications far beyond general relativity. These mathematical tools have found applications in diverse areas of physics and mathematics, demonstrating the power of fundamental research to generate unexpected benefits. The energy conditions and singularity theorems that govern the formation and properties of event horizons have provided crucial insights into the nature of matter and energy. The positive energy condition, weak energy condition, and other constraints on matter and energy emerge naturally from the requirement that general relativity produces sensible predictions. These conditions have implications for cosmology, particle physics, and our understanding of the fundamental forces. The study of event horizons has also highlighted the importance of symmetry in physics. The no-hair theorem, which states that black holes can be characterized by just a few parameters, reflects deep symmetries in the laws of physics. The breaking of these symmetries through quantum effects, as seen in Hawking radiation, provides insights into the relationship between classical and quantum physics. As we conclude this exploration of event horizons, it becomes clear that these remarkable features of spacetime represent far more than simple boundaries around black holes. They embody the cutting edge of human knowledge, the limits of observation, and the deepest mysteries of the universe. The event horizon stands as a testament to the power of human curiosity and the mathematical tools we have developed to understand the cosmos. The journey from the first theoretical predictions of black holes to the direct observation of their shadows illustrates the remarkable progression of human understanding. Each generation of physicists has added new layers of complexity and insight to our understanding of these objects, revealing connections and implications that were previously unimaginable. The event horizon has evolved from a mathematical curiosity to a fundamental feature of our universe, one that continues to challenge and inspire new generations of researchers. Perhaps most remarkably, the study of event horizons has revealed that the most extreme objects in the universe are governed by the same fundamental principles that apply to everyday physics. The laws of thermodynamics, the principles of quantum mechanics, and the geometry of space-time all come together at the event horizon in ways that illuminate the deep unity underlying the apparent diversity of physical phenomena. The questions raised by event horizons remain among the most profound in all of science. What is the ultimate nature of space and time? Can information be destroyed? Is our reality fundamentally holographic? How do quantum mechanics and general relativity fit together? These questions, sparked by the study of black holes and their horizons, continue to drive research at the frontiers of physics and philosophy. The event horizon represents both an end and a beginning. The end of classical spacetime as we understand it, and the beginning of a new realm where quantum effects and gravitational physics merge in ways we are only beginning to comprehend. It stands as a boundary, not just in space, but in human knowledge itself, marking the limits of what we can directly observe, while pointing toward deeper truths about the nature of reality. As we continue to probe these cosmic boundaries, with ever more sophisticated tools and theories, the event horizon will undoubtedly continue to surprise us, challenge our assumptions, and reveal new aspects of the universe's fundamental nature. It remains one of the most compelling examples of how the universe is far stranger and more wonderful than we could have ever imagined, a reminder that the greatest mysteries often lie at the boundaries of our understanding. As we stand at the threshold of this cosmic mystery, the event horizon continues to challenge every assumption we've held about the nature of reality itself. What began as a mathematical curiosity in Einstein's equations has evolved into perhaps the most profound testing ground for our understanding of physics, consciousness, and existence. The journey we've taken through the physics of event horizons reveals something remarkable about the universe we inhabit. These invisible boundaries don't just mark the point of no return around black holes. They represent the fundamental limits of knowledge, observation, and perhaps even meaning itself. When we peer into the cosmic abyss, we're not just looking at distant astronomical objects, we're confronting the very foundations of what it means to know something about our universe. Consider the profound implications of what we've discovered. The event horizon forces us to abandon our intuitive notions of space and time as fixed, absolute quantities. Instead, we find ourselves in a universe where time can stretch toward infinity, where space itself can be curved beyond recognition, and where the very concept of inside and outside becomes meaningless. This isn't merely an academic exercise, it's a fundamental restructuring of how we understand reality. The information paradox stands as perhaps the most significant challenge to our current understanding of physics. The idea that information might be permanently lost when it crosses an event horizon strikes at the heart of quantum mechanics, which demands that information must be preserved. Yet general relativity seems to suggest otherwise. This isn't just a technical disagreement between theories. It's a crisis that demands entirely new ways of thinking about the universe. The holographic principle offers one of the most startling potential resolutions to this crisis. If information about a black hole's interior is indeed encoded on its two-dimensional surface, then we must radically revise our understanding of how information and reality itself are structured. This suggests that what we perceive as three-dimensional reality might be nothing more than a projection from a lower dimensional boundary, a concept that challenges our most basic assumptions about the nature of existence. The implications extend far beyond black holes themselves. If the holographic principle is correct, it might apply to the entire universe, suggesting that all of reality as we experience it could be encoded on some distant cosmic boundary. This would mean that the event horizon isn't just a feature of black holes. It's a window into the fundamental architecture of spacetime itself. The thermodynamic properties of black holes have revealed deep connections between gravity, entropy, and information that we're only beginning to understand. The discovery that black holes have temperature and entropy has forced us to recognize that these seemingly simple objects are actually among the most complex systems in the universe. They contain more entropy than any other object of comparable size, yet they appear completely featureless from the outside. This paradox points to something profound about the relationship between information and geometry. The fact that a black hole's entropy is proportional to the area of its event horizon rather than its volume suggests that space itself might be granular at the smallest scales. This has led to new theories about the quantum nature of space-time and the possibility that space and time themselves might emerge from more fundamental quantum information. The observational breakthroughs of recent years have transformed event horizons from purely theoretical constructs into observable phenomena. The event horizon. Telescopes' images of black holes have provided our first direct glimpses of these cosmic boundaries, confirming many theoretical predictions while raising new questions. The detection of gravitational waves from black hole mergers has opened an entirely new window into the behavior of spacetime near event horizons. These observations have revealed that event horizons are not static, unchanging boundaries, but dynamic features that can merge, oscillate, and evolve. When two black holes spiral into each other, their event horizons eventually merge in a process that sends ripples through spacetime itself. These gravitational waves carry information about the merger process, providing new insights into the nature of these cosmic boundaries. The technological advances that have made these observations possible represent a triumph of human ingenuity and international cooperation. The Event Horizon Telescope required coordination between observatories across the globe, pushing the limits of what's possible with current technology. Similarly, the gravitational wave detectors represent some of the most sensitive instruments ever built, capable of detecting distortions in spacetime smaller than a fraction of a proton's width. Looking toward the future, we stand on the brink of even more revolutionary discoveries. Next-generation gravitational wave detectors will be able to observe black hole mergers with unprecedented precision, potentially revealing new physics in the strong field regime near event horizons. Space-based telescopes and interferometers will provide new ways to study these cosmic boundaries, possibly revealing signatures of quantum gravity effects. The theoretical landscape continues to evolve as well. String theory, loop quantum gravity, and other approaches to quantum gravity all make different predictions about what happens near event horizons. Future observations may be able to distinguish between these theories, potentially revolutionizing our understanding of the fundamental nature of spacetime. Perhaps most intriguingly, the study of event horizons has begun to reveal deep connections between physics and information theory, suggesting that the universe might be fundamentally computational in nature. If this is true, then event horizons might represent the ultimate information processing boundaries, where the universe itself performs calculations that determine the flow of information through spacetime. The event horizon stands as both a boundary and a gateway, a limit to classical physics and a doorway to new understanding. It represents the edge of the known universe in the most literal sense, marking the boundary between the observable and the unknowable. Yet it also serves as a beacon, guiding us toward new physics and deeper truths about the nature of reality. As we continue to probe these cosmic mysteries, we're not just learning about black holes or event horizons, we're discovering fundamental truths about the universe we inhabit. The event horizon has taught us that reality is far stranger and more wonderful than we ever imagined, and that the boundaries of knowledge themselves might be the most fertile ground for discovery. As we reach the end of our journey through the mysterious realm of event horizons, we find ourselves standing at the intersection of humanity's greatest intellectual achievements and our deepest cosmic mysteries. The event horizon represents far more than just a boundary around black holes. It embodies the very limits of our understanding and serves as a bridge between the familiar world of classical physics and the strange quantum realm that governs reality at its most fundamental level. Through decades of theoretical work and recent observational breakthroughs, we have transformed the event horizon from a mathematical curiosity into a tangible reality that we can study, measure, and even photograph. Yet, with each answer we uncover, new questions emerge that challenge our most basic assumptions about space, time, and information itself. The implications extend far beyond black holes. The holographic principle suggests that our entire universe might be encoded on a distant boundary, fundamentally altering how we perceive reality. The information paradox forces us to question whether the universe truly preserves all information, or whether some knowledge can be forever lost. These aren't merely academic debates, but profound inquiries into the nature of existence itself. As we continue to develop more sophisticated instruments and theoretical frameworks, the event horizon will undoubtedly reveal more of its secrets. Future missions, advanced gravitational wave detectors, and perhaps even quantum computers may help us finally resolve the paradoxes that have puzzled physicists for generations. The event horizon stands as a testament to both human curiosity and cosmic mystery. It reminds us that the universe still holds secrets waiting to be discovered, boundaries waiting to be explored, and fundamental truths waiting to be understood. In studying these cosmic points of no return, we push the boundaries of knowledge itself, ensuring that our quest to understand the universe's deepest mysteries continues to drive us forward into the unknown. And now, as we slowly return from the edge of the unknown, let this remind you that the universe still holds secrets far beyond what we can see or even imagine. The event horizon isn't just the boundary of a black hole, it's the boundary of our understanding. Thank you for joining me on this quiet journey tonight. I just wish that you made it till the end of this long journey and hope you have a wonderful and an amazing night. Until next time, stay curious, keep wondering. This is Boring Science signing off. Cheers.